Hello everyone. So today we'll discuss a very famous problem from the LeetCode, which is jump game 2. It is commonly asked in the interview round, so it's very important problem to solve. So let's go through the problem once. Like, we are given an array of a non-negative integer numbers, and you are initially positioned at the first index of the array. Each element in the array represents your maximum jump length at that position. Your goal is to reach the last index in the minimum number of jumps. You can assume that you can always reach the last index. So in the we are given an array of non-negative integers, and every number represents the maximum jump length which we can make from that given index. So as an example, from the 2, the maximum length jump which we can make, it's 2. Basically minimum means it's in a range of 1 to 2. So 1 can be, if we jump one step from the 2, it will be on 3, we'll land into 3. If we jump 2, we'll land into this one. Okay, so in this way we need to reach the last index, which is 4, and in the minimum number of jumps. So let's see how we can solve this problem using multiple ways. So yeah, the first one is the recursive approach. So in the recursive approach, what we have initially is that we are initially positioned at the first index of the array, and our goal is to reach the last index. So how we can do? From 2, we know like maximum length jump which we can make is from in a range of 0 to 2, in range of 1 to 2. So if I make a one length jump, I will be landing into this position, and the second I can make in here. So let's see, when we reaches making a one length jump, we'll be reaching at 0. So from 0 we will be making a jump of length 0, which is actually we will be staying in this index only. We'll be not going any far from this 0. So there will be no solution possible from this given index. So considering, like, if we have to take this index, we as a starting point, we will not be reaching the end of. Okay, so this is not the part of the solution. So if you go, and from the 2, if you go to 1, so from 1 we have only one maximum, only one length we can jump. So in this case we can jump it to 4, and from 4 we can maximum jump 4 length. So as the length of the array means we only have two more two more indexes which need to be visited. So in this scenario, from 4 I can jump here, or 4 I can jump here. If there are other elements, we can also jump till maximum 4 length. Okay, so in this scenario I'll be jumping to 1, and be jumping to 6 as well. So once I jump to 6, I will be reaching the last index, which is the goal of the problem, is to reach the last index. So in this way I can reach here, and if I jump to from 4, if I jump to 1, from 1 also I can reach to 6. So the number, if you count the number of steps to reach this and this, so will be 1, 2 and 3. So there are 3 jumps required to reach it here, and the same way if we count this, it will be 4. So the minimum is 3, so we have to return the minimum of all the possible answers. So this is one of the way how we can solve the problem. The second way is using the time complexity of this problem is like n to the power n, because we are recursively calling again and again to check is there a possible solution exists for a given position where we are currently right now. So it's a very time complexity problem. So what we can do, we can basically reduce the time complexity using a DP. So what in DP we have a given array. So what is the basic goal of this, how we can solve using a DP, is basically we at a given index, wherever we are, we need to check how many minimum steps required to reach that index from the initial point. So the starting here is that I have my I pointer pointing to the first element, and the j pointer pointing to the 0th element, and the maximum ij should be less than equal to I. Okay, so so what is the minimum number of step I can reach here? So this is my DP. So initially I am positioned at 0, so the minimum, there is no jump required here, so it's a 0, and the rest I filled with a maximum number, which is infinity here. So once from 0 means from 2, I can jump here in one step, and I can also jump here in one step. So I filled my DP using 1 and 1. Okay, so same way, what is the minimum number of step I can reach here? 4. So I cannot reach it from here because it's 0, no jumps allowed here. So from here I can reach. So the minimum number to reach here is 1, and to reach here is 1 plus 1, so which is 2. Okay, the same way the minimum number of steps to reach here is basically from the 0th index I have to go till here. From here I will go to 4, and from 4 I will go to 1. So the maximum is 3 here. 3 number of jumps is required. And for this element also, like from 2 I can go to 1, 1 I can go to 4, from 4 I can have I can go to 6 as well. Like I can make a 2 jump here. Not it's not required to go from 1. We can also make a 2 jump. So the minimum number of jumps required is 3 in this case. So yeah, so using DP we can also solve the problem. The only constraint here is that for any given index, suppose I am here, I have to calculate from the 0th and check what is the minimum number to reach it here, reach this given index. Okay, so this is the second approach. It will be more clear when we go through the code. And third one is the greedy approach. So this is the, oh yeah, in the DP the time complexity is n square because we will be running a 2 for loop, one on the initial n and second on the constraint will be there from j0 till I, means less than I. Okay, and the third approach is the greedy approach. So in the greedy approach, what we have basically is at a given index we want to calculate how far we can reach, what is the current farthest we can reach, and what is the current end we have till now. So at the given starting position we will be current end is actually 0 and current farthest is also 0. But as I can see from 2, the as we start iterating from 2, the maximum I can reach here. So my current farthest will be this, I can reach here. Okay, and the same way from here I will check what is my current farthest, how far I can reach, so till here, and from here I can see how far I can reach. So this is basically a kind of we know the boundary, like for a given if you are positioned at a given index, what is the boundary till I can reach, what is the farthest boundary I can reach. Same way for the same way you also know your end, like what is the current end where you actually can go. Okay, so this problem basically evolves around like finding the right boundary, and once you have the boundary, you know you can reach the boundary from any element, means at a means a given element inside that box. Okay, so this will be more clear when we go and look into the code. So I'll be jumping into the code now. So in the code, the first approach, as I said, is a recursive approach. So in the recursive approach, we have positioned at a given index. So initially we are positioned at the first 0th index. From 0th index we will check what is the maximum steps I can take. Okay, so I know the maximum step is actually the number which is placed at that given index, so which is basically 2. If we consider this example, we have 2 as a number. So from 2 I can basically reach to 0 and 1. So that I'll be doing, I'll be making a baby step here. Baby step means means start iterating from 1 till the number should be less than equal to 2, and I'll be making a baby steps, and from the baby steps I'll be calculating what is the minimum length, and recursively I'll be calling this method, and this method will give me the minimum length. I'll be means saving the minimum length in the minimum jump, and I'll be returning the minimum jump from my recursive method. So this will be the recursive approach. So in the DP approach, so DP, as I said, the j should be less than I, and for each and at any given index we'll start calculating what is the minimum number of step to reach that given index from the 0th index. So this is the logic for that. And if you check, and initially we mark the base condition is that whatever the index we are initially at, we will be there are 0 jumps to required to reach there, so initial index will be 0, and this way we can have like the minimum number of jumps required to reach at a given index. Okay, this is a very straightforward code. If you run it, you'll get to know. And the third approach is actually the greedy approach, and in this case we know how far we can reach, the current farthest and the current end. So using this we will be calculating the boundary till where I can reach, and from that given boundary I will be again going and checking what is the next boundary where I can reach, and this way we will be able to calculate how many minimum jumps is required to actually go and reach the end. So this code means it's not very means sometimes it becomes difficult to understand, but when you run the code and keep a dry run and check, you'll be able to get what is the greedy approach basically doing here. Yeah, so that's pretty much about this problem. And like, this is a very simple problem, but it's sometimes it has become difficult to think and get the solution out of it. Even sometimes like I also faced, and I have seen multiple people also facing issue in the recursive approach as well. But yeah, that's a simple problem, but yeah, it's a very commonly asked interview question, so that's why I wanted to discuss. So yeah, thank you for listening.